Hello everyone, this is Pritika Patel working as an assistant professor in Computer Engineering Department of Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. Today in this session we are going to discuss about algorithm for traversal of graph, which is the topic of subject data structure of second year third semester. Now coming to the point, traversal of graph. Traversal of a graph means visited each node and visiting exactly once. Simply, traversal of graph is nothing but we have to visit all vertex of graph at least once. For traversing of graph, there are main two techniques which are used. First one is DFS, that is depth first search, and second one is BFS, that is breadth first search. Now first one is DFS, depth first search. It is like pre-order traversal of tree. So DFS is nothing but the just like pre-order traversal of tree. In DFS, traversal can start from any vertices Vi, and Vi is visited, and then all vertices adjacent to Vi are traversed recursively using depth first search. DFS is an recursive algorithm. It is use stack data structure. DFS visit every node of a graph depth wise. Right? Now rule for depth first search. Rule number 1. Put the starting vertex into the stack. Then mark it as visited. Then display it. Now rule number 2. If stack of top has adjacent unvisited vertex, then visit the adjacent unvisited vertex and mark it as visited. Right? So now here in rule number 2, we have to check the stack top. Right? Top value of stack we have to check, and this vertex having adjacent unvisited vertex, then we have to visit the adjacent unvisited vertex and mark it as visited. Then push it into the stack and display it. Right? Else pop top element of stack. Right? So if condition is false, then else part is execute and pop top element of the stack. So topmost element of stack is pop from stack. Repeat rule number 2 until stack is empty. This rule number 2 is repeated until stack is empty. Right? So this is the rules for depth first search. Now example of depth first search. Here one graph is given which having vertex A, B, C, D, E, F, G, H, I and G. Right? And for DFS we have used stack data structure. Right? So here one stack is already created, then one display array is used for display the vertex of DFS. Right? Now starting from rule number 1. Rule number 1 says that put the starting vertex in the stack. Put the starting vertex into the stack. So here suppose we take A is in starting vertex, right? So put A into the stack. So here A is put into the stack, right? Then mark it as visited. So mark this A is visited, right? Then display it. So here A is display, right? Now rule number 2. If stack of top, right? Now here A is inserted into the stack. So top is pointed over here, right? So stack of top is this, right? Now check that A has adjacent unvisited vertex, right? Here A has B, C and D as an adjacent unvisited vertex because A have directly connected with B, C and D, right? So now visit the adjacent unvisited vertex and mark it as visited. So now visit this adjacent unvisited vertex and mark it as visited, right? Push it into the stack. Now push this B into the stack and display it. So here we can display B, right? Now again check if stack top. Now this B become a top of the stack, right? So now check stack of top. So topmost element of stack is now B. So now check B has adjacent unvisited vertex. Yes, B have this E and F is adjacent unvisited vertex. So visit the adjacent unvisited vertex, that is E, right? Then push it into the stack. So now push E into the stack, right? And display it. So here display E, right? Now again this E become a top of the stack. So again check rule number 2, topmost element of stack, that is E. Now check E has any adjacent unvisited vertex. Now here no vertex is there. So else part is execute of rule number 2. So in else part, pop top element of stack. So from here we have to pop this E, right? So now again this B become a top of the stack, right? Now again check stack top has adjacent unvisited vertex. Now top of the stack is B. B have any unvisited vertex? Yes. Here F is a adjacent unvisited vertex. So visit this vertex F and mark it as visited, right? Then push it into the stack. So now push F into the stack and display F. So here we can display F, right? So now again this F become a top, right? So now again check stack of top has any adjacent unvisited vertex, but here no adjacent unvisited vertex. So else part is execute. So else part is that pop top element of the stack. So from here we have to pop this F, right? So now again B become a top of the stack, right? So now again check stack of top has any adjacent adjacent unvisited vertex. No. Now B has no any other adjacent unvisited vertex, right? So again else part is execute and pop topmost element of the stack. So from here B is pop from the stack. So now A will become a top of the stack. Now check stack of top, that is A, having any adjacent unvisited vertex. Yes, there is C and D, which is adjacent unvisited vertex. So visit the vertex C, right, and mark it as a visited. Then push it into the stack. So now C is pushed into the stack and display it, right? So now this C become a top of the stack. So now again check stack of top has any adjacent unvisited vertex. Yes, Here G is there, which is the unvisited vertex. So visit it and mark it as visited, right? Then push it into the stack. So G is pushed into the stack and G is display here, right? So now this G become a top of the stack, right? Now again check that G having any unvisited vertex. No, here no vertex are there. So there is no unvisited vertex, right? So else part is execute. So pop top element of the stack. So from here we have to pop this vertex G, right? So now again this C become a top of the stack, right? Now check C have any unvisited adjacent unvisited vertex. No, there is no unvisited vertex. So again else part is execute. So we can pop this C from stack, right? So now again A become a top of the stack, right? So now again check A have any unvisited vertex. Yes, there is a D, which is a unvisited vertex. So visit it and mark it as visited, right? Then push D into the stack, right? And display D, right? Now D become a top of the stack, right? So now check D having any unvisited vertex. Yes, D having two unvisited vertex, that is H and I, right? So now visit this adjacent unvisited vertex H and mark it as visited. Then push H into the stack. So here H is pushed into the stack and display H, right? So now H is become a top of the stack, right? So now again check stack of top has adjacent unvisited vertex. Yes, there is a adjacent unvisited vertex G, right? So visit this vertex J and mark it as visited, right? Then push it into the stack. So J is pushed into the stack and display G, right? So now this J become a top, right? Now again check of the top, that is J having any adjacent unvisited vertex. No, there is no adjacent unvisited vertex. So X part of rule number 2 is executed, right? So pop topmost element of the stack. So J is pop from here, right? So now H become a top of the stack, right? So now check H having any adjacent unvisited vertex. No, H having no adjacent unvisited vertex. So now again else part is executed. So topmost element of stack, that is H, is pop from here, right? So now D become a top of the stack. So now check D have any adjacent unvisited vertex. Yes, there is a I, which is unvisited, right? So we visit this vertex I and mark it as visited, right? Then push it into the stack. So right, put I into the stack and display I, right? Now I become a top of the stack, right? So now again check stack of the top, that is I, having any adjacent unvisited vertex. No, there is no adjacent unvisited vertex, right? So else part is executed. So pop top element of the stack. So topmost element here is I. So I is pop from the stack, right? Now D become a top of the stack, right? So now check, D has having any adjacent unvisited vertex? No, there are no adjacent unvisited vertex, all vertex are visited, right? So again else part is executed and topmost element of the stack have to pop, right? So D is pop from here, right? So now A become top of the stack, right? So now check, A has any adjacent unvisited vertex? No, there is no adjacent unvisited vertex, all vertex are visited, right? So now again else part is executed and pop top element of the stack, that is A, so pop A from the stack, right? So now this display is nothing but the output of depth first search, right? So A, B, E, F, C, G, D, H, J, I is the answer of depth first search, right? Now algorithm of DFS. First of all, we have to initialize top and visited. So visited is initialized with 0 and top is initialized with 0, right? Now step number 2, push vertex into the stack, right? So push V for push vertex into the stack, push algorithm is used and vertex is pushed into the stack, right? Now step number 3, repeat while stack is not empty, right? Now this step number 3 is repeat until stack is not become empty. Now repeat step 3 while stack is not empty. So pop vertex and push it, store it into the V. If visited array is 0, then visit V as a 1 for all W adjacent to V, right? So here for vertex, all adjacent vertex we have to find, right? If visited visited vertex W is 0, then push into the, then push it and end of the if for statement, and here end of if statement. So this is the algorithm of depth first search. Now next is breadth first search, that is BFS. Breadth first search is breadthwise motion and use Q data structure. So in BFS we are going to go through breadthwise, right? So breadthwise motion is used in BFS, and for BFS we are using Q data structure, right? BFS is an iterative algorithm. BFS visits every node of a graph level wise, right? So in BFS we are visiting each and every node by level wise, right? So now rules for BFS. Rule number 1, visit the starting vertex and mark it as visited, right? Then display it and set a pointer to the starting vertex, that is currently working vertex. Then rule number 2, if currently working vertex has adjacent unvisited vertex, then visit the adjacent unvisited vertex and mark it as visited, right? Insert it in a queue, right? So NQ operation is performed on this queue, right? And display it. If condition is false, then else part is executed. So in else part, update the pointer to the first element of queue, right? Then remove the first element of Q. So here DQ operation is performed. And repeat rule number 2 until Q is empty. So this rule number 2 is repeated up to Q is become empty. Right? Now example of BFS. Here one graph is given which having vertex A, B, C, D, E, F, G, H, I and G. Right? Here one Q is already drawn which we are used for breadth wise motion, that is breadth first search, and one array is used for display the vertex, right? So now start from rule number 1. Visit the starting vertex and mark it as visited, right? So here we are going to start from here. So A is a starting vertex and mark it as visited, right? And display it, right? So here A is display, right? Now set a pointer to the starting vertex. So currently working vertex is set as a A, right? Now rule number 2. If currently working vertex has adjacent unvisited vertex, right? Now A is a currently working vertex, right? So A having any adjacent unvisited vertex? Yes, that is B, C and D, right? So now visit the adjacent unvisited vertex, right? So we are going to visit this B and mark it as visited, right? Now insert it in a queue, right? So here B is inserted into queue, right? And displayed. So B is display here, right? Now again check currently working vertex has any adjacent unvisited vertex. Yes, there is a adjacent unvisited vertex, that is C. So again visit this vertex C and mark it as visited, right? Then insert it into a queue. So again C is inserted into the queue, right? And display it. So C is display over here, right? Now again check rule number 2. If currently working vertex has adjacent unvisited vertex. Any adjacent unvisited vertex? Yes. There is D which is unvisited. So visit it and mark it as a visited, right? Then insert it in a queue. So D is inserted into the queue, right? Then display it. So D is display here, right? Now again check that currently working vertex A having any adjacent unvisited vertex? No, there is no unvisited vertex. All the vertex are visited. So now else part is executed. So update the pointer to the first element of Q. Now first element of Q, that is B. So now currently working vertex become a B, right? And remove the first element from Q. So remove this B from Q, right? Now check currently working vertex, that is B having any adjacent unvisited vertex? Yes, that is E and F. So now visit this E and mark it as visited, right? Then insert it in a queue. So E is inserted in a queue, right? And display it. So here E is display, right? Now again check currently working vertex B has any adjacent unvisited vertex? Yes, that is F. So visit it and mark it as visited. Then insert it in a queue. So F is inserted in a queue, right? Then display it. So F is display over here. Now again check currently working vertex, that is B, have any adjacent unvisited vertex? No. Now there is no unvisited vertex. Show else part is execute. So update the pointer to the first element of Q. Now first element of Q is become C, right? So this C is become a currently working vertex, right? And remove the first element from Q. So now remove the first element of Q, that is C, from the Q, right? So now again check currently working vertex C has any adjacent unvisited vertex. Yes, that is G, right? So now visit this vertex G and mark it as visited, right? Then insert it in a queue. So G is inserted in a queue and display it, right? Now again check C has any adjacent unvisited vertex? No, there is no vertex which is unvisited, right? So else part is executed. So now update the pointer to the first element of Q. So now D is the first element of Q, right? So currently working vertex become this D, right? And remove D from this Q, right? Now check if currently working vertex has adjacent unvisited vertex. Yes, D having H and I, two unvisited vertex. So visit this H and mark it as visited. Then put this H into the queue and display it, right? Now again check that D having any adjacent unvisited vertex. Yes, there is I is unvisited, so visit it and mark it as visited. Then put I into the queue and display I, right? Now check that D having any unvisited vertex. No, now there is no unvisited vertex for D, right? So else part is executed, right? So update the pointer to the first element of Q. Now first element of Q, that is E. So now currently working vertex become E. Then check this currently working vertex E has any adjacent unvisited vertex. No, there is no unvisited vertex. So update the pointer to the first element of E. Sorry, here whenever the E become currently working vertex, then next step is what? Remove the first element from Q, right? So now currently working vertex become E, right? So now E has no adjacent unvisited vertex. So we have to update the pointer to the first element. So now first element, that is F, right? So F is selected as an currently working vertex, right? Now remove F from the Q because this is in the rules, right? Now check F having any adjacent unvisited vertex. No, there is no adjacent unvisited vertex. Show else part is executed. So now again update the pointer to the first element of Q, right? So G become a first element of the Q. So G become a currently working vertex. So G is removed from here, right? Now check G having any adjacent unvisited vertex. No, there is no adjacent unvisited vertex, right? So now again else part is executed, right? So update the pointer to the first element of Q, that is H, right? So H is become a currently working vertex, right? And H is removed from Q. Now check H having any adjacent unvisited vertex. Yes, that is J. So J is marked as and visited and put it into the queue and display it, right? Now again check H having any adjacent unvisited vertex. No, there is no adjacent unvisited vertex. So again update the pointer to the first element of Q, that is I. So I is become a currently working vertex, right? So now I is removed from Q, right? Then check I having any adjacent unvisited vertex. No, there is no adjacent unvisited vertex. So again update the pointer to the first element of Q, that is J. So now J become a currently working vertex, right? Now J is removed from Q, right? Now our Q become empty, right? And this step number 2 is repeated until Q is empty, but now Q is empty. So this step is stop here, right? And this display is become a answer of BFS, that is breadth first search. So answer is A, B, C, D, E, F, G, H, I and J, right? Because breadth first search is nothing but the level wise search or level wise motion. So A is first, then B, C, D, then E, F, G, H, I and then G, right? So this is the example of breadth first search. Now algorithm of BFS. Step number 1 is initialize queue and visit it. So initially visited array is 0 and front and rear both are 0. Now mark visited of V as 1. So visited vertex is set to 1. Add vertex V to Q. Step number 3 is add vertex V to Q. So now insert Q. Here insertion of vertex into the Q, for this insert Q is use. Step number 4, repeat while Q is not empty. So this step number 4 is repeat until Q is not become empty. So remove from Q and that is stored into the vertex. For all vertices W adjacent to V, right? If visited W is 0, then visited W set 1 and insert Q W, right? So this is the algorithm of breadth first search. Thank you.